The Cubli is a reaction wheel-based inverted pendulum which has potential applications in both space and the medical field. By using the Cubli mechanism, a satellite could change its orientation without using fuel-based thrusters, potentially increasing its time in orbit. Additionally, the Cubli mechanism could also be used in assisted mobility devices where balance is required, such as exoskeletons for stroke patients. The principal operating mechanism for the Cubli is changing position based on rapid angular acceleration and deceleration of a flywheel. However, since the device cannot maintain its position at unsteady points of equilibrium without assistance, a controller is necessary. The mechanical design of the Cubli is quite simple and consists of 5 different components. On the figure to the left, it can be seen that the housing is made from laser-cut plywood, riveted together for structural rigidity, and contains mounting options for the remaining components. The reaction wheel is a 4-inch diameter aluminum disc for a high moment of inertia. The motor is connected to a planetary gearbox with a 3-to-1 reduction to provide more torque to spin the flywheel and also limit the maximum angular velocity of the flywheel to 6,000 RPM. Lastly, an IMU sensor is utilized to determine the angular position of the cube. The microcontroller and power source are not included in the model as they will be outside of the cube during operation. If these were placed within the cube, the mass center of the device would be shifted away from the central axis of the flywheel, increasing the complexity for a controller. The figure on the right shows the complete model with internals hidden within the housing to prevent damage during operation. Root locus plots were created for P, PI, and PID controllers. These indicate that all 3 controller types have at least one closed-loop pole on the right-hand plane, making the system unstable. In addition, the magnitude of the poles and zeros are in multiples of 100, which are considered to be larger than expected. As a result, as seen in the next clip, the PID simulation did not stabilize. The linear quadratic regulator is a type of optimal control that is based on state space representation. By changing the values of the Q and R variables, the optimum gain set will change. This consequently determines the position of the closed-loop poles of the system and the responses of the system. 3 trials were attempted in finding the optimum gain set. While the Q matrix is constant, the R values are 1, 0.001, and 0.0001. The simulation of trial 1 below shows that the measured angles detected are too minuscule for the simulation to show distinct movement. The step responses for all 3 trials report measured angles that are at least a factor of 10 to the negative 4th away from the desired angle. Even though slightly lower values for the measured angles were expected, the results allude that the measured angles were disturbed too much. The error of the closed-loop system should have been kept low, since the state variables in the Q matrix were penalized. By changing the plant parameters, the closed-loop pole should be closer to the origin and the results should be improved. The pole placement method chooses a unique pole location and solves for gain set values. In order to implement this method, the system must be controllable. By calculating the magnitude of the controllability matrix, the Cubli system is controllable. Thus, the pole placement method can be used. 3 pole placement cases have been tested. As the poles are placed further away from the imaginary axis, the values of the K matrix had a decreasing trend. Case 2 appears to have the most fitting resemblance to the desired angle and is simulated in the next clip and shows stability. As seen from the figures in the previous slide, the measured angles were a factor of 100 less than that of the desired angle. This resulted in a lack of noticeable motion in the simulation. For future improvements, we would use a direct drive motor with a smaller mass and less friction as a result of removing the planetary gearbox. Reducing these parameters would result in more realistic gain values. Additionally, a brake could be implemented to increase the consistency of jumping to an edge. Plant parameters could also be changed or verified to get the Cubli to start from a face. This simulation shows the Cubli starting from a face and jumping up before being stabilized by a working controller. With significant changes and improvements to the design of the Cubli, balancing on the vertex of a cube could become a possibility.